This is our last type of hypothesis testing. For this, we are returning to a topic from early in the course, linear regression models. What was linear regression? The situation here is a data set with two numeric variables. We want to know if there's a relationship between the two numeric variables. This is, in fact, the first test we've done with two numeric variables. All of the previous were two categorical or one categorical and one numeric. With two numeric variables, the relationship between them is the most natural question. A linear regression is a theory that there is a linear relationship between the variables. Here's data from an earlier video about possum head length and total length. We generated a linear model using least squares regression. That process suggested an intercept of 41 and a slope of 0.59. The slope meant that for every centimeter long the total length of the possum is, the head length also increased by 0.59 centimeters. So what does it mean to statistically test a linear model? The model has two coefficients, a slope and an intercept. Typically, the letters m and b are used here. We'll focus mostly on the slope, since the slope really captures the relationship, how much one variable increases or decreases in terms of the other. What would a null hypothesis be about this relationship? Well, it would say that there is no relationship, that, in the population as a whole, the two variables are completely independent. The alternative hypothesis says that there is a linear relationship, that the slope coefficient is non-zero. This is a reasonable setup. The least squares regression for our sample produced a slope of 0.59. The question is the same as always for hypothesis testing. How likely is it that the 0.59 slope was just due to randomly taking a sample that happened to have this slope? If the population has no linear relationship, but random sampling could randomly show some relationship, how likely is it to get the 0.59? That likeliness, as always, leads to a p-value, and therefore an assessment of whether our sample is statistically significant to give evidence for a linear relationship. I've stated the alternative hypothesis that the slope is non-zero, which leads to a two-sided test. You could also argue that the slope could be positive or negative, which would be the same hypothesis testing, but only a one-sided test, leading, as usual, to a p-value that differs by a factor of 2. So we have a hypothesis, and we have a test statistic, the slope generated from our sample. We need a distribution to use to evaluate this test statistic. The central limit theorem does apply here, and the slopes generated from random samples under the null hypothesis can be expected to be normally distributed. However, as usual, there are conditions. What are the conditions here? First, we have an independence condition. That might seem odd. Aren't we trying to establish a relationship between two of the variables? Isn't that the opposite of independence? That's true, but this independence is not between the variables, it is inside the variables. The length of one possum shouldn't directly alter the length of any other possum. The cases need to be somewhat independent. Second, the data needs to be reasonably structured. For this pair of variables, the residuals are the best way to understand the structure. The residuals should themselves be roughly normally distributed. What this means is that notable outliers in the residuals can mess with the mathematical models. Other strange patterns in the residuals can also present problems. The residuals should look like they are distributed sort of equally above and below the linear regression, and should not be strangely clustered or grouped. I can look at the residual plots from Learning Outcome 9 to evaluate these residuals. Here are the residuals for the possum data. The residual plot looks like it should satisfy the conditions. The residuals are scattered reasonably around the line, with no significant outliers. Here's another residual plot. I also expect this to work well with the mathematical model for hypothesis testing. It's a reasonable scatter of points, and there are no significant outliers. This is a residual plot that I would expect to work poorly with the central limit theorem and the mathematical models for hypothesis testing. There's too much of a pattern here, even though there are no outliers. What this pattern might tell me is that a linear model is probably not the right model for this. In the entire setup for this video, we are implicitly assuming a linear model. However, even when two numeric variables are related, that relationship is often nonlinear. The conditions in this section are partially set up to try to identify data sets where the relationship might be nonlinear, and where testing a linear hypothesis is not necessarily a profitable approach. Here's another residual plot. The problem here is the distribution of the points. Though they are scattered reasonably above and below the line, there is one strange outlier. The outlier happens to be on the line, so it probably fits the linear model, but it can still have a detrimental effect on the probability theory behind the hypothesis testing. And finally, here's a more extreme example. This is an outlier that certainly presents a problem and will convincingly upset the mathematical probability structure of the sampling distribution. That's conditions. As before, our approach here is qualitative and informal, but hopefully it still makes sense. We're using the residual plots to try to identify data sets where the linear hypothesis is reasonable and the hypothesis testing can proceed. Now we proceed to the hypothesis testing. This is done with t-tests and t-distributions. Like with means, using numerical variables leads to choosing t-distributions over normal distributions. The more substantial tails tend to give better probabilistic outcomes. We did a t-test by hand previously, but the details for two numeric variables are more complicated, so, like with the ANOVA from the last video, we let the software do the test for us. In the background, the software is generating a distribution with the appropriate degrees of freedom parameter, generating the sample statistic, the slope, from the data, and assigning it a t-score and a p-value. If I ask R to do this hypothesis test, it reports the following. First, the test statistic it is using is 0.5729. This is the slope of the linear model in the data, though it is slightly different from the 0.59 from the start of this video. Probably there is some subtle adjustment in the least squares regression. We can still proceed with this test statistic. Then R gave the test statistic a t-score of 9.657. This says that our sample produces a slope that is 9.657 standard deviations, or standard errors, out from the mean of the sampling distribution. Finally, R also gives the p-value for this, which is a minuscule 4.68 times 10 to the negative 16. Even doubling this for a two-sided test, this is still well below any threshold. And this is perhaps not surprising, since visually, the data did strongly look like a linear relationship. Confidence intervals can also be generated for this slope. The process is the same, using the slope of the sample as the mean for the sampling distribution. Again, a t-distribution is used, and R calculates the range of that t-distribution that covers 95% of the randomly generated samples. In this case, R reports that I can be 95% confident that the slope of this relationship is between 0.4553 and 0.6906. This matches with the hypothesis testing. A slope of 0, the null hypothesis, is nowhere near this confidence interval of the slope. I did this all for a slope of a linear model. The same thing can be done for the intercept, and the process is basically the same. The test statistic, the intercept that the sample implies, is 42.7. Again, this is a bit different from the original linear model, likely due to subtle mathematical adjustments in the algorithms. Then R calculates a t-score and a p-value. And again, the p-value here is very significant, showing evidence that this is a linear model with a non-zero intercept. Finally, this is all for a single explanatory variable. In previous learning outcomes, I also presented linear models with multiple explanatory variables. R can handle this as well, and will do some of that work in the class activity.